Okay, I think they start recording. Okay. Hello, hello, hello. Hello. The one on Zoom can hear me, right? Hello? Okay, okay, can. Okay, then we start now. Okay. So, yeah, today is the final session of steel. So I'll be covering basically what we have not covered in the last two sessions. So web buckling, tension members, and connections. B-split, I've heard is not in sight, right, this year. Yeah, it's just for info. So I'm not sure. That's what people told to me. So basically, we'll cover last if we have time. So yeah, let's focus on the three. Then yeah, as usual, I'm still selling my cheat sheet for $10. If you want, just PM me. If you're making your own cheat sheet, just make sure that it's to the point that you don't need to think when you do the checks. Okay, if you're making yourself, just make it like tidy. Okay. Okay, so before we start, just some general notes. So for finals, right, your time will be very limited. So just perform the checks which is needed. If they ask for LTV, just do LTV. No need to do anything else. If they ask for tension check, just tension check. Okay? That's one thing to take note because your time will be like really, really tight in your finals. And then for the second thing, right, is for LTV checks, sometimes the prof like to give a table for MCR. So yeah, the prof will teach LTV, right? Usually they give a value of this. They already give the value of this very big thing, which is if you see the MCR value, right, for LTV, it's this portion. So you just need to take from the table the value, just plug it in, then multiply by C1. Okay, so yeah, this one you check the back of the paper first, see the appendix what they give first. Sometimes they will give this table. Yeah, so you don't need to waste time or calculate like, all these things because this thing is very very tedious. Okay, so those are the two things that I want to say. Yeah, once again, time is key. So when you do the questions, try to time yourself. And yeah, as usual, before you can design something, you must get the loadings right. So if you haven't been able to get the loadings right, please practice it. Yeah, like get the correct design loads. So this one, right? You can refer to the first session. It's the tributary loading, and also of course, the BMD and SFD. So these two, right? You must be able to get it right. And actually, one more is the column. So column, you remember there's the distribution of moments between floors. Um, Actually, yeah, just a bit of recap on quiz two. I think I think some people made this mistake also. So yeah, before we even start, I'll just give a context. So for example, you get a moment of 60, for example. Some people they divide the 60 into three floors, like 20, 20, 20. This is wrong. You only divide the 60 between two floors. Okay? Because the beam is connected to the column above and below only. So the moments will be distributed. So if this is 60, 30 will go on the top column like this. So this is 30. The bottom column also receive 30. Okay, just for I just thought of this because I think I heard a lot of people they divide the 60 with three floors. That's not correct. So yeah, so this one is under the design loads for the column. Yeah, so do practice the tributary loading, BMD, SFD, and also the columns. Okay, and this one I think I'm not sure if it's still applicable for this year because I heard there's a change in prof. So last year they asked us to print the whole section property table to like this thing. So with all the values. Yeah. So this thing. Yes. So I'm not sure if this year they require, but I prefer to still print just in case. Okay. So that's everything that I need to say, I think, for the notes. Yeah, so I guess we can go to the questions directly. So for the first question, right, is web buckling. So this is what we skipped in the first session because it's not under coverage. So for web buckling, right, for context, this is applicable when there is a concentrated force, okay? Concentrated or point force. So if you have a I beam, for example, this is your I beam, something like this. If this is your I beam, so when you put a force on top, right, like a point force, the web, so the web means this part, right, the middle part, it can buckle like this. So this one we consider as a failure. Okay, the web buckles this way. Okay, so we need to check for this buckling. So we need to make sure that the beam doesn't buckle when we put some force. So this concentrated or point force, it can be from the external load. It can also be from the reaction forces. Okay, it can be both from external load and reaction forces. Because technically reaction force is also a point load. So it's considered under the check. Okay. So here's an example from 2021. So now you have a heavy equipment. They give you the stumps of the equipment, which is the support. It's measuring 200 by 200. This one is a typo. This one is supposed to be mm. Okay, so 200 by 200 means this thing is 200 by 200. Okay, and then they ask us to check the adequacy of the beam web resistance. Okay, means they ask us to check this. Okay, in locations G and H. Yeah, so just that. So we can do the check. So part A. Okay, so part A. First things first, before you can check something, you must get the design load first. Okay. So they're asking for the point load at G and H. So if you see here, G, the point load comes from the object, from the block, from the heavier equipment. Okay, it goes like this. In F, there's also a point load, but we only ask to check G. Okay, like G. There's also at point H, there's a reaction force. So there's a force going upwards. So these two forces are the one they ask you to check. Okay, so let's find these two forces first. So first things first, your heavy equipment is, what's the weight? They give this one already. 500 kilonewtons. It's a factored design action. Okay, keyword here, factored. So means partial factors have been applied. Okay. Okay. Remember, there's the raw loading and there's the process loading, the one which you have multiplied by the partial factors. If it's factored, means they have already multiplied for you. You don't need to multiply by 1.35 anymore. So in this case, we know that FG is just 500 divided by 2. So 250. Because 500 here is split into 2, right? So F here is 250. G here is also 250. Right? Okay. So we have 250, 250. Now how about H? So if you see here, there's a 3 reaction forces. So here, here, and here. But usually we assume these two portions are simply supported. So it's easier to analyze. Okay, so now assume simply supported. So assume simply supported. So therefore FH is 250. So 250 comes from where? So remember we have 500, right? This is 500. So this is 250, 250. Okay. So if you notice, this part of the beam is symmetrical. So 250 here will be carried by FE. The other 250 will be carried by F8. Okay, that's why here is 250. Okay, or you can do also since this is 500 the loading, so you just divide by 2, so it's 250. Okay, but if you notice, H also supports this part of the beam. Okay, the right side of the beam. So now we have 60 kilonewtons per meter. Okay, that's the UDL. So this UDL will be split into two as well, into this one FH and also this part, call it C, for example, so FC. Okay, so you need to add how much? So 60, that's the UDL, multiplied by the length, which is 8, divided by 2, because it's split into C and H. Okay, so 60 times 8 divided by 2. So therefore, your FH is 490. Okay, so that's your forces. Okay, so now we have FG and FH, right? Then we can do the check. So for this check, usually we do it one by one. So we do it for one point force first, then the other point force. Okay, I'll put something like this. Okay, so let's do for point G first. Let's do the check for point G. Okay, so for the first step of checking, right, is to identify the load type. Okay, so for web buckling, there are 3 load types. There's type A, B, and C. So yeah, before I proceed, let's clarify what's type A, B, and C first. Okay, so if this is your beam, this is other beam, this is your beam. Okay. This one is in your lecture notes and also in the Europe. So I think you can refer to that. Okay, type A, if this is your force, and yeah, so this type A. So it's located in the middle of the beam. Then we have type B. So for type B, right, it's for anything that have 2 forces in both sides. So like this is type B. Okay, then for type C is located near the end of the beam. So this is type C. Okay, so these 3 types you need to take care of. And then just for info, the force is usually spread on this like area. So we call this area is like we call this SS. This one is also SS. This one is SS. Okay, it's like the bearing location of the force. It's where the force lies on. Okay. Then for type C, we have this also, which is C. Yeah, so these are just some parameters. This one you can see again in the Eurocode, there's this, so you can refer to the Eurocode. Okay, so if you go back to this example, where's point H? Oh, sorry, point G. So point G is here. Okay, point G is located in the middle of the beam. Okay, it's nowhere near the end of the beam, and also it's only one force going up. It's not like this. If there are like 2 like this, then it's type B. But since there's only one force from the top like this, we call it type A. Okay, so like this. Okay, so this one is FG. So this one is type A. Okay, for type A, there's a calculation for KF. So KF in this case is 6 plus 2 HW divided by A squared. So in this case, it's 6 plus 2. Then what's HW? So HW is, we need to refer to the beam first. So it's UB 533210. Okay, so yeah, so take your section properties table. find universal beam, then go to 533. Okay, 533, 210, and 82. Okay. So for HW, you can approximate it as H minus 2 times TF. Yeah, so divided by 8. Okay, so just for context, if this is your IB, so this whole thing is H, this small thing is TF. Okay, that's why it's H minus 2 TF. So you get your HW. Okay, so now we have this. So A is the distance between stiffeners. Okay, A is distance between stiffeners. So distance between stiffeners. So okay, let's go back to this. So if you have a stiffener like this, if you have stiffeners like this, then this is A. Okay. So what are stiffeners? If you draw your beam in 3D, wait, did I draw it in 3D already? Yeah, yeah. So like this. Okay. Copy this. Okay, just for context, is stiffeners are some plates that you put in the middle of the beam. So something like this. Okay. So they put it like this. This is they put like a slit there, okay, like a plate in the middle like this. It's to stiffen the web. Okay, so that's what a stiffener is. Okay, you can see it if you see like a beam in the middle, like yeah. Later, if you see like I beams like in the construction site, right? You can see like those stiffeners. Yeah, but anyways, if you see in this image, there are no stiffeners, right? If there are no stiffeners, we put A as infinite. Okay, if there are no stiffeners, so A is infinite. Okay, if A is infinite, then this becomes 0. Okay, so your TF is just 6. Yeah, okay, that's correct. So now that's done. Let's go to the next step. So far clear, right? Okay. Okay, so after finding KF, you can find FCR. So this one is just follow the steps already. FCR in this case is just 0.9 KF times E times TW divided by TW cube divided by HW. So again, this one you need your um, properties table. So KF in this case is 6. E by default is 210, 1, 2, 3. This one is in megapascals. So Newton per millimeter squared. Okay, and then your TW here is yeah, this one you need to find your table. Okay, so it's again 533 210 82. So 533 210 82. Yeah, 9.6. Okay. I'm afraid I copy wrong here. Okay. Then HW, as I explained before, is just H minus 2TF. So 528.3 minus 2TF. So TF in this case is 13.2. Okay, so this one is in millimeter squared. Okay, because this one is millimeters cube divided by millimeters. So if you want to change it to kilonewtons, you just divide this by 1000. Okay, then you get kilonewtons. Okay, so 0.9 times 6 times 210 times 9.6 cube, then 58.3 minus 2 times 13.2. 2. So you get 1999 kilonewtons. Okay. You see here it's F, right? FCR. So it's a force. Okay? It's a critical force. Okay, so now we have FCR. Next step is to calculate M1 and M2. Okay, so M1, in this case, we calculate as FYF times PF. This one is FYW divided by PW. So FYF, FYW, what are these? So remember your beam, we have the flange, we have the web, right? So this one sometimes, so the flange, right? So this flange, this is FYF. So it's the yield strength of the flange. And that's FYF. FYW is the yield strength of the web. Because sometimes for I beams, right, we like to weld the web and the flange if it's not controlled. Right? Sometimes, okay. So that's just in the case where the web and the flange are from the two different plates, and apparently they have different that's called they have different strengths just in case. Okay, but in this case, right, since the whole beam is, I think S275. Oh, sorry, S355. Yeah, the whole beam is S355. So both the flange and the web, they are of grade S355. So this one can cancel out because they are the same, they are the same grade. It's for this case, yes, it's usually the same because hot roll it's one piece. Yeah, but yeah, this formula is just the case if you have three different plates, you put it together as one beam because that's common also. Okay, but for your case, it's mostly hot roll, so usually it's the same. Okay, so this one because it's S355. This one is also S355. Okay, so now we just find BF. So BF is your B. So that's 208.8 divided by TW. So TW is 9.6. That's your M1. Then M2. M2 is 0.02 HW divided by PF squared. I keep forgetting the square for this stuff for some reason. Okay, but this one, then HW just now we found is this thing. It is HW divided by TF. So TF just now is, oh, we don't have it. I think it's 9.6. Oh no, it's 13.2. 13.2 squared. So in this case, you will get M2. So let's calculate the M1, M2. This is 8.8 divided by 9.6. This one is 21.75. 0.02. Up to 8.3 minus 2 times 32 squared. So you get 28.9. Okay, so that's M1 and M2. And then for type A and B, you follow these steps. So Ly. Before find Ly. I write here type A and B, right? Because both type A and B they use these steps. For type C, they have another step. Okay. For type C, I think you need to calculate LE first. LE equals something, something, something. Then just follow the steps. Okay. But since ours is type A, let's follow these steps. So Ly is equals to SS plus 2TF. Then you have 1 plus square root of M1 plus M2. Okay. So Okay, let's focus on SS first. So just as I drew just now, SS is the bearing of the force. It's where the force is located. Okay. So for this one, for point G, you need to look at where the force is at. Okay, so if you notice, for the force G, the bearing plate or the bearing surface is this. Okay, is that surface. Okay, so we know from the info, this one is 200, right? Okay, like this plate is 200, this bearing force. This one from here, 200 mm by 200 mm. So your SS is 200. Okay, so SS in this case is 200 plus 2 times TF. So just plug in the values. 1 plus square root of 21.75 plus 28.9. Okay, so now you have 300 plus 2 times 2. You have 414.3 mm. So notice the unit is in mm. You can see here, because this one is length, mm. This one is also length, mm. Okay, so the unit of Ly is mm. Okay, so now you have Ly. Okay, so now you have Ly. You can go to the next step. So this one is lambda f. So lambda f in this case is square root of Ly, which is 414.3, then times TW. Okay, actually I'll write the formula first. So Ly TW FYW divided by FCR. And this should be bigger than 0.5. Okay. So Ly in this case is 414.3. TW, I think it's 9 point something. 9.6, yeah, thanks. 9.6. Then FYW, just now it's grade 355, right? 355 divided by FCR. So FCR in this case was 1999, or 2000. Okay, this one we convert to SI units, so times 10 to the power of 3. Okay, so for 4.3. Okay, thanks. 0.84. Okay, so it's bigger than 0.5, so it's okay. If it's lower than 0.5, use 0.5. Okay, so this is like a minimum value. Okay, so now we have this. Okay, so the rest of the steps is straightforward. We make a new page. Okay, so after lambda f, you need to find chi f. So chi f. So this one is 0.5 divided by lambda f. Okay, so it's just 0.5 divided by 0.84. So in this case, you have 0.595. So this is your reduction factor. Then find length effective. So L effective. In this case is chi f L1. Okay, chi f L1. So 0.595. You multiply by the Ly just now is 414.3. So you have 246.6. Okay, so now you have L effective. Calculate FRD. Okay, find the resistance. Okay, we are already at the resistance now. So in this case, we have FYW, line effective, then EW, all divided by gamma M1. FYW is 355, line effective is 246.6, then TW is 9.6, all divided by gamma M1, which is 1. Okay, this one is Newton per millimeter square. This one is millimeter square. So you just times 10 negative 3. You get kilo newtons. Okay. Yeah, yeah, so 840, right? 840.4 kilonewtons. Okay, so now we have this. Okay, so now we have two checks. Okay, so first thing is lambda, sorry, not lambda, what's this? Oh, eta, I think this is eta. Eta 2. Okay, eta 2 first. So this one is FED divided by FRD. FED in this case is, what's FED? FED is 250, right? 250 divided by 840.4. So this case is 0.297. So this one must be less than 1, so it's okay. Okay, then for the second check, I think it's lambda 1. So lambda 1 in this case is, oh, this one is in combination for your moment. Okay. MED divided by FYWPL divided by gamma M1, M0, gamma M0. Okay, since this one, right, we don't have time, usually you can stop at this step, okay. Okay, but by right, you need to by right, you need to find the moment at that place. By right. So if you have time, find the moment. If you don't have time, just leave it like that. Okay. But the final check should be this one. Eta 2 plus 0.8 eta 1. So this one should be less than 1.4. So this one is the combined check. Okay. So that's how you find the web buckling. Okay. So these steps are, yeah, quite straightforward actually. Usually people get it wrong here. Just type A, type B, type C. Okay, so make sure you know which case is which. Okay. So let's go to the second point, which is point H. So for point H, so the steps are exactly the same, right? Let me see. Okay, so if you see point G and point H, both of them are type A because it's in the middle of the beam. Okay, it's nowhere near the end of the beam. Oh, wait, let me turn off the notification for this one first. Okay, now let's continue first. Okay, so yeah, so again, FH is located in the middle of the beam, right? So FH is type A. Then for type A, the calculations are the same. So KF is the same for FH. FCR is also the same because there's nothing changing here. M1 and M2 is the same. So everything is the same until this part, the L1. Okay. Okay, so I'll write it down first. Everything the same up to L1. Okay. Did I forget something? I think I forgot something. Ah, yeah. Sorry. I forgot something. It's this one. Sorry, I got mistake. Okay. It's a mistake in the explanation. Okay. If this is lower than 5, okay, if lambda f is lower than 5, lower than 0.5, you set M2 to be 0, then repeat steps. Yeah, repeat from Ly. Okay. Yeah, I forgot. If yeah, so this one is just one condition. Okay. So means if your value here is less than 0.5, you need to repeat from Ly, but you set M2 as 0. Okay, you ignore this. You split this 0. Okay, if it's lower than 0.5. But since this is bigger than 0.5, just continue. Okay. So this is only if. Yeah, I made a wrong explanation as well. Okay. Okay, let's continue first. So point H, everything is the same up to Ly. So Ly, the formulation is like this. Let me copy. Okay. Okay. So for Ly, right? Okay, TF is the same, M1 is the same, M2 is the same. But what's SS? So remember, SS is your bearing width. If you go back to the image, FH, the bearing width is this I beam. Okay? So for I beams, there are special calculations to calculate the bearing width, like this SS. Okay, there's a special calculation for it. Okay, so for this SS, as you can see, right, the force is transferred from this U beam. Okay, so the U beam you calculate for SS is this. Okay, so use this for SS. Okay, it's not this beam. This beam is the beam that we're checking. Okay, the beam we're checking. Okay, the beam we're checking means all the formulas here, right? HW, TF, TW, right? It uses this beam. Okay, the beam that we check. It's only for SS. So only for SS, we use this one, the transfer beam. Okay, so this one is only for SS. Okay? Because SS has nothing to do with the beam we're checking. It has things to do with the bearing width. Okay, that's why we use this one for the SS. So, okay, let me type it down. So SS in this case uses UB 610.178 UT2 for SS. Which one let me cut and paste. Okay, so for a I beam, the SS is TW plus 1.6 R plus 2 TF. Okay, so this one again, you refer to this beam for SS. So TW in this case is use your table. So go to 6110, 6110, 178 PT2. So TF is 12.8. Sorry, TW is 10. TW is 10 plus 1.6 times R. So R in this case is 12.7 plus 2 times TF in this case is 12.8. Yeah, this one you can practice looking from the table. Yeah? So, well, so what's SS? So 10 plus 1.6 that's 12.7 plus 2 times 12.8. So in the end, we will get 55.92 millimeters. Okay, so this one just copy paste. So copy, paste, put it in SS. Okay, so in the end you will get 80.92 plus 2, 13.2, so you have 270.2. Okay, so now you have this. Okay, so just the rest of the stuff are the same, just different values. Okay, so let me check on this one. Okay, so this one just copy paste. Okay, but change LY. LY is now 270.2. Then TW stays, because TW is to, okay, TW is not, it's not this beam, it's the beam that we checked. Okay, that's why TW stays. So in this case, we have 270.2 times 9.6, which 3.5 divided by 199. We get 0.679. So quite close to 0.5, but still above, so it's okay. So we continue the next step. So yeah, these steps are the same. Okay, but change this one is 0.679. So we use that value for this. And this one changes, LY changes also. LFF changes, TW stays the same. FRT changes, FPT changes. Yeah. Okay, so just fill in the values lah. So 0.5 divided by 0.679, we get 0.736. So 0.736 times LY. Remember LY changes to 270.2. So you get 198.9. Okay, so LF equals 198.9. 3.5 times 198.9, 1.6 divided by 1000, you will get 677.9. So 677.9. FED for this case, right? FED is 490. So 490. Okay, so 490 divided by answer, you will get 0.723. So it's lower than 1. It's okay. Then, as usual, by right, you need to do this check. But we don't know the moment, right? Actually, for this one, we know. Because it's at the support, right? And we assume it's simply supported. So M is 0. Okay? So in this case, we know this one is 0. Okay? Because MED is 0. So your combined check, in this case, is just 0.732. Sorry, 723 plus 0.8 times 0, which is just the same, which is 0.723. This one is definitely less than 1.4, so okay. Okay, so done. Let me move to this. So done. That's web buckling. That's everything already. Okay, so most of the time they can only change uh, the configuration of the loading. Okay? But the steps are exactly the same. Okay, as usual, it's just a matter of getting the loading right. Okay, so yeah, I hope you practice on that. And then what else? Be careful with SS, because SS sometimes they give you two beams like this, then you use the other beam for the other beam. So be careful with that. And oh, actually, that's part B also. So regardless of the design check, suggest a practical solution to reduce the risks of web bearing and buckling. So actually the answer is here, I've drawn it already, is to add stiffeners, that's it. Add stiffeners. Because this will stiffen the web so it doesn't buckle as easily. Okay, so this one is part B. Let's label this part B. So done. That's the whole thing. Are there any questions so far for this? Okay, for the you can see other examples in the CE Club solution. Yeah. Because I think the year after this they have Type C, so you can try Type C as well. Okay, yeah, but the steps are mostly the same. So yeah, it's okay. Just they have only like one more step, I think, like to find LE. Yeah, yeah, just to find LE. Okay, so that's number 2 of the exam done. Wait, I'm not sure how you determine the cases. Again, case A is for the force which is in the middle of the beam. Okay. Then for type C is for the force in the end of the beam. Type B if there are two forces on top and bottom. Okay. So for this one, again, I'll explain. Type G is located in the middle of the beam. It's like you see the right and left, right? It's very far from the end. Then you see point H, you see the left and the right, it's also very far from the end. So both of them are type A. It doesn't need to be strictly at the middle, as long as it's relatively far from the end. Yeah. So I'll just draw examples for type C and type B like this. Okay, so for example, we have something like this. We have this. We have this. Okay. I'll give you an example like this, for example. Okay, so for this one, right, you can see here, if, for example, this equipment, then this is your beam, then these are your columns. It's okay. Okay, so if you have something like this, right, there's a force from going from the top, from the stump of the equipment, from the equipment. There's also a reaction force going from the bottom. So this is type B. Okay, even though it's located in the edge, right? Type B is usually more critical. Okay, so this is type B. Another example, for example, is if you have something like this is your B. For example, you have some loading here. For example, this is your W, which is a UDL. Then this is your support. For example, like this, so this one is column. So this one, you have a reaction here, right? So this is the force. Okay, so this is type C because there's only point force going from one direction. Okay, so this is type C. So if you notice, this one, the UDL, so this UDL is not considered it's not considered under the web buckling check. Okay, why is it not considered? Because it's distributed. It's not a concentrated force. Okay, so only concentrated force matters. Okay, I hope this clears up the type A, type B, type C. Okay, so wait, so somebody asked, can you consider F type C? No, F is not type C. F is type A. Again, you need to look to the left and to the right. Okay, F, right? There's nothing on to the left and to the right, so it's type A. This one, this point E, this one is definitely the type C. Okay, because it's located at the end of the beam. Okay, this one is still type A. Sorry. Um, this one. This one is type A. The UDL on top doesn't matter. Yeah, UDL is not considered a point force, so it's not type B. Okay, so again, FH, even though there's a UDL on top, UDL is not considered a point force. Okay, so there's only one point force going from one side. Okay, so FH is type A. This one is type C, not type B. Remember, UDL is not counted. Okay, so I hope this clears up the type A BC. Okay. Yeah, I think that's everything. I hope that's everything. Okay. So that's all for web buckling. So we can go to the next topic. I think we can take 5 minutes break as well. So maybe 11:05 we go back. Okay. 11:05. Okay. Okay. So I'll pause the recording as well. Okay. Wait, let me see. We have this. Yeah, so I guess we can start now also, continue. Okay, so we've covered web bearing, right? So usually the format, right, is question one is usually LTG, question two is usually web bearing, question three is usually column, then question four is usually connections. So connection includes bolts, welds, and also tension members, usually these three. Okay, so that's our focus now. I'm still I'm still deciding whether should I do this or should I do the other one. Okay, let's do this one first. I think this one they have everything. Yeah. So okay. So let's see the question first. So we have a circular row section. It's welded into a 12 millimeters cassette plate using 6 mm welds, and it's also bolted for to a plate which is two numbers of M24 class 8.8 non-preloaded bolts, grade S275. Okay, then the steel is grade 275. They are subjected to tension action of 260. Okay, so first things first, show that the two bolt group is sufficient in terms of shear and bearing resistances. So usually we usually look at the details of the members first. So they're asking about the bolt, right? They're asking the two bolt group. So it means we're looking at this. Okay, and then we have what we call the shear and bearing resistance. So shear first, right? Shear means you slide the thing, okay? So if you have an object like this or bolt, so shear means you have one force going here, the other force going here. So it will slice through the thing. Okay, it will feel like this. Okay, this is your shear failure. Okay, the thing slides. Okay, so this one is F, this one is F. Okay. Okay, so yeah, that's visible from here. Is your plan view. So it fits like this. It is part A. It also says bearing resistance. So what's a bearing resistance? So bearing resistance is if you have a bolt like this and you have a plate, you have a plate going this way, right? Okay, this is your plate. Okay, let me draw it in 3D. I can visualize it to you. Like. Okay, imagine this is your plate, this is your bolt. So when you pull the bolt, this bolt will hammer down onto the plate. Okay? It will hammer the plate. Okay, that's our bearing force. Okay, so it will hammer down to this area of the plate. Okay, this area. Okay, so if you see it from the top view, it will form something like this. It will crack this way. It is our bearing force or bearing resistance. Okay, this is part A. Okay, so this one is shear. This one is bearing. Okay, usually bolts they only have these two, shear and bearing. Okay, so let's do the shear check first. Okay, so shear first. So shear check. So you have M24 plus 8.8 S275. So this is your bolt. Okay, so this one is your bolt. So for this one, right, for bolts, usually we go directly to the table. Okay, there's a calculation way, there's also the table way. But for S275 bolts, right, this one we can go to the section properties table. Okay, go to the bolt section, go to the non-preloaded, okay, non-preloaded bolt. So you will find there's the FBRD. So from table, you can obtain FBRD. So V stands for shear, okay? V stands for shear. So RD is just design resistance, okay? Resistance, design. Okay, so go to your table, open class 8.8. Where is it? Class 8.8 non-preloaded. Okay, so practice yourself, practice yourself like looking at the table. Okay, here M24, right? 24 is the diameter of the bolt. Okay, okay, this one means the diameter of the bolt is 24. Okay, so your FBRD, you should get 136 kilonewtons. Okay, this one is based on the table. Okay, then we see how many bolts do you have. We have, yeah, we just directly use the table. We don't need to calculate. Okay, we can calculate, but that takes more time. So let me see. Yeah, this one is the calculation. Hmm. Okay, I'll do both. I'll do both. So you can do this, or you can do FVRD equals to alpha V FUB A divided by gamma M2. So it's a bit longer, right? That's why usually I just do table. So this one is alpha V is 0.6. FUB in this case is 800. Then A is area of the bolt, so 24. 5 over 4, 24 squared. Then all divided by gamma M2. which is 1.25. So this should give you a similar answer. Should. I actually, well, so long never used the formula method. Wait, you get 174. Wait, wait. Alpha V, FUV, A times divided with MT. Give me a second, let me see. Sorry? AS? Yeah. Oh, yeah. Use a tensile stress area. So this one is 353. Let me see. Is it the same? Yeah, you get 136 or something. Yeah, so this one also use table. Okay, it's not 20. It's not 24 apparently. So A use table. So either way, you need to use the table. So, yeah, so you can just take FBRD directly. Yeah, because either way, you need to take A from the table also. So these two ways you can do, but usually I'll take FBRD directly. Single shear and double shear. I think it's easier to see later in the second, like second example. Okay. 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 So, yeah, let's continue. So now we need to consider two things. Okay, we need to consider two things. One, is it single or double shear? Okay, I'll just explain how single or double shear. Two is how many bolts are there? These two, okay? Okay, so these two things you need to consider. Okay, so for single shear or double shear, you must look at the bolt cross section. Okay, how many shearing planes are there? So if this is your bolt, if this is your plate, for example, like this, for example, like this, okay, basically you need to see where the bolt fails. Okay, you need to see where the bolt fails in the shear. So for this image, it only fails. Wait, wait, let me make it nice. Let's make this blue so it's obvious. Okay, something like this. This is bolt. Okay, this is plate one. This one is plate two, for example. Okay, you must see the cross section. Where does it fail? In this case, it fails only in this one line. Okay, so if it only fails in this one line, it's a single shear. Okay, in the case that we have something like this, for example, you have a bolt now like this. Okay, now imagine your cross section looks like this. Then you have this. Yeah, the plates. Then you have like this. Okay, so this one is plate one, plate two, uh, plate three. Yeah, so now if you see, right, um, sometimes they are not plates. They can be gusset plates. They can be like pin connections. So there are a lot of cases. The key here, right, is just to look at the elevation view. Look at the plan view. You see where does the bolt feel in shear. You count the number of shearing planes. Okay. This one you put it this way. This one you put it this way. Well, for this one you put it this way. This one you put it like this. Okay, so ignore the F. The F you can ignore actually. What I want you to focus is actually on this side. Okay, so if you pull it like this, the bolt will shear here, it will shear here. Okay, it will fill in these two positions. Okay, then this is a double shear bolt because they have two locations for failure. Okay, so if we go back to the image just now, for example, this image, you see the elevation Q. There's one plate going that way, one plate going this way. So the shear failure plane is here. For this bolt, it's the same here. So these two bolts are single shear bolts. Okay. So uh, that. Okay, so total resistance, so total shear resistance in this case is so two bolts times one because it's single shear times the FD RD. So this one is the number of bolts. This one is single shear. This one is just your um, shear resistance per bolt. So from the table, right, they only give us FVRD. This one is per bolt. So one bolt resists this much force. If you have two bolts, then it resists twice the force. Okay. So this is just 2 times 1 times your FVRD, which is 136. You will get 272. Okay. This one is bigger than your 260, right? Okay, so bigger than BED, which is 260. So this one is okay. So very simple, right? Just from the table, multiply a bit, then you get VRD only. Next one is the bearing resistance. Okay, so bearing resistance. Okay, so bearing resistance. Okay, for bearing, this one is up to your preference, but I don't like to use from the table. I like the table for it only for shear. Because if you look at the table for bearing, right, it's a bit hard to read. Yeah, thickness of ply, edge distance, end distance, pitch, gauge. Yeah, this one, uh, I rather just calculate manual for this case for bearing. Okay, so for bearing, there are some steps. So step one is to find FUB divided by FU. So, oops. So FU here stands for the ultimate. Wait, there's the yield strength and the ultimate. I think ultimate stress lah. So ultimate stress. So B here stands for bolt. Okay, this means the FU here is the property of the plate. Okay, this one is of the plate. This one is the property of the bolt. Okay, so be careful. Okay, like that. So this one, because if you go back to the definition, the bolt is pushing against the plate. That's why you need to compare the strength of both the bolt and the plate. If the bolt is stronger than the plate, then yeah, it's a bit risky lah. That's why we need to take this ratio. Okay, but in this question, it's just nice. I think both are S275, right? So S275 FY is 275, but FU is you need to check the table, yeah. check the table. This one you will get 430. See? This is the same table where you get the FY. You can check, okay? I don't know if you can see, but it's this table. Okay, this table. You can see this table. Yeah, this one. Yeah. So that's where you get the FU. So this one is 430 divided by 430. So it's just 1. Because both the bolt and the plate, they have the same grade. Wait, really? Oh, wait a second. Oh yeah, you're right, you're right. Oh, oops. Oh man, this FUB is 800. Sorry. Oh, okay. Wow, that's dangerous. Okay. Okay, so apparently FUB and FU is not from the same table. Okay. So 430 and 800. Okay, so that becomes 1.86. Okay, I'll write this down. It's not from the same table. Okay. Okay, thanks for the seat. This one I forgot already. Okay, so now you have FUB and FU. So now you calculate the alpha D. So this one we go back to the inner and edge and yeah, those things like. So I'll clarify first. If you have a group of bolts, then this is your force. Okay, we have two criteria. Okay, we need to check the bolts parallel to the force and perpendicular to the force. Okay, let's start with the parallel first. So for parallel, these ones are the, what do you call it? End bolts. Yeah, these guys are the end bolts. The rest, so these guys are the inner bolts. Okay, this for the direction parallel to the force. For the direction perpendicular to the force, we also have a set of inner and edge bolts. So these guys are the edge bolts. And these guys are the inner bolts. Okay, so we can have inner bolts. We can have inner and edge. So we have inner edge, and inner, or and edge. So we have 4 combinations, depending on where the bolt is. Okay. There are 4 combinations. So if you look at this image again, so for this one, right? For this bolt, it's the end edge. This bolt is inner edge. Okay? And because it's located at the end of the member. So this is your plate, right? You see this one is located at the end. This one is inner, okay? Because this is at the end of the member. Okay, this one is the end, this one is the inner. And then perpendicular to the force. So we're looking at this direction. Looking at this direction. Both of these are at the edge. Okay. So take your time to look at the image. But now we have one end, one edge, one inner, one edge. Okay. Okay, so parallel. Okay, let's do parallel first. So parallel to the force where n volts, so alpha d. So we have n here, inner. Alpha d here is E1. So E1 is, so this one is E1. So it's the edge distance to the bolt, to the first bolt. Then we have the E1. Okay, so this one is E1 divided by 3 dO. Then this one is P1 divided by 3 dO minus 1/4. And I forgot to clarify one more thing. This 24, wait, where is it at? Yeah, this 24 is the diameter of the bolt. Okay, for the diameter of the hole, okay, so for, okay, did I write it? So the, I think I wrote it somewhere, but, yeah, there, okay. Okay. So for bolt diameter, if it's less than, okay, bolt diameter is labeled as D. Okay, hole diameter is labeled as DO. This one is DO. If your bolt diameter is less than 24 mm, DO is D plus 2 mm. Okay, if it's bigger than 24, its DO is equals to D plus 3. Okay, there's also a third category of bolts. It's called the holding down bolts. This one I think is very rare. Like in our case, holding down bolts. This one is DO equals to D plus 6. This one is in mm, mm, mm. Okay. So in this case, since our bolt diameter is 24, we use this one. Okay. DO equals D plus 2. Okay, that's our bolt diameter. Okay, so in this case, so E1, what's E1? Let me see E1. E1 is 60. E1 is 80. So 60, 80, 60. This one is 60. This one is 80 divided by 3 times 24 plus 2. Okay, so we use 26. This one also we use 26. So this one minus 1/4. Okay, so we have 60 divided by 3 times 26. So this one is 0.769. Then we have 0.776. It is for the parallel direction. Now we have the perpendicular direction. Perpendicular direction, we are only interested in edge bolts. So we just need to find the edge ones, the edge cases. Okay, so for edge cases, so key one is the minimum of, okay, let's find 2.8 first. So 2.8 times E2 divided by DO minus 1.7. So in this case, it's 2.8. What's E2? Let's go back to the picture. So E2 in this case is this distance. So it's 70, right? So 70 mm. So 70 divided by 26 minus 1.7. So in this case is 2.8 times 70 divided by 26 minus 1.7, 5.84. Is it? Wait, 70, yeah, 70. Okay, so this one is bigger than 2.5. So we use K1 equals to 2.5. Because K1 is the minimum of this thing or 2.5. Okay, you can see the lecture notes or Eurocode. Okay, it's a bit complicated, but there's a lot of if else. So yeah, just need to prepare your cheat sheet well. You get a lot of cases. Then alpha B is supposed to be the minimum of those things. Okay, so alpha B is the minimum of alpha D, which is this 0.769, FUD over FU, which is 1.86, or 1. So in this case, the minimum is 0.769. So we use this value for alpha B. It's the same with the inner bolts. So for inner bolts, we use 776. Okay, so that's alpha B. So now we have this. Okay, we have alpha B, we have K1. Now we can find FBRD. Okay. So now let's find FBRD. FBRD is the sum of the sum of FBRD, basically. Okay, of each bolt. So okay, FBRD of bolt 1 plus FBRD of bolt 2. Just now we identified the bolt 1 as end edge. Just now we identified bolt 2 as inner edge. So in this case, the formula for FBRD, right, is K1 alpha B, K1 alpha B, FU D times T divided by gamma M2. So let's plug it one by one. Okay, let's do the FBRD one first, which is the end edge case. So end alpha B is 0.769. K1 is 2.5. Okay, so that's K1 times alpha B times FU. So FU is 430, I think. Wait, let me check. FU is 430. Then times D. D is the bolt diameter. So that's 24. Then T is the thickness of the member. Okay, let me write down. So a lot of things, bolt diameter, plate thickness. Okay, so plate thickness in this case is 12 mm, yeah? 12 mm, 12 mm. Okay, so 12 mm, okay, times 12. So that's K1 alpha B FUDT divided by gamma M2. So for gamma M2, right? Gamma M2, let's use 1.1. So this one I'll explain. So gamma M2, so this gamma M2, I don't know which prop you want. Like, I don't know what the prop wants, honestly. Because gamma M2 can be 1.25, can be 1.1. The 1.25 is the EC2 default value. And then Singaporean value, we use 1.1. 1.25, okay. Okay, can. So this one, we need a. Okay, so in practice, we use 1.1. Okay, because of course we need to stick to the Singaporean code. But for the Euro code, which is like the base document, we use 1.25. Okay, but since they asked to 1.25, okay, let's do 1.25. Okay. Because I don't know, each prop is different. Okay. Okay, someone asked, the edge bolts parallel to the force. I thought it's the furthest bolts at the end. Wait, I'm confused. It's so parallel to the force, there's only end bolts and inner bolts. Then for the this one. End bolts, inner bolts, the edge bolts, inner bolts, edge bolts. Okay, never mind, we continue first. Continue first. Okay, so this one is FBRD1. So we find FBRD2. So FBRD2 in this case, the key one is still 2.5, but the alpha B, right, we use 0.776. Okay, then the FU is the same, D is the same, T is the same. Okay, so we're done. So we just need to find the value. So in this case, we get 383 kilonewtons. So this one is bigger than your FBRD, which is 200 and something, right? 260. So it's okay. So done. Both check done. Okay. So both done. So what's next? Let's see. Determine the tension resistance of the CHS and the gusset plate. Okay, so what does this mean? So the CHS is instead of feeling at the bolt, we can also feel when we pull a member very hard. Okay, it can feel like this. Okay, it can feel like this. So you break the CHS apart. That's possible. Okay, so this is part B. You can also break the plate apart. So the plate rips. Okay, so it's here. Okay, if you see the plan view, it looks like this. So this one, or this. Okay, so you pull the member so hard to the point that it breaks. Okay, actually this one is like this. This is more like this. It fails usually at the bolt. Okay, because the bolt will drill a hole. Okay, so part B. So for part B, okay, it's the tension resistance of the CHS. Okay, let me see. Tension members. Okay. Okay, let's start with the CSS. We compare it to the plate. The CHS was the member size. It's 114.3 times 6.2. Then the plate is, the thickness of the plate is what? 12 times 140. Okay, 140. Okay, some people, they might be confused on the dimensions. Okay. So to clarify, right? This is your CHS. This is your CHS. You're pulling it this way, right? So the area which is in tension is this area. It is area you're trying to find. For plate, your plate looks like this. Your plate looks like this. See? Then remember, you also have two bolts in the middle. You drill some hole into it, right? So there's a hole here. Okay, there's a hole there. Something like that. So you have like this. Okay, in the exam, you don't need to draw this nice line. This one I'm just trying to show. Okay, so the area in tension, since your force is going this way, So your area is this. Okay, this is what we call A net. Okay, again, this one, right? If we compare it to the image from the top, oh, ayo. Copy, paste. Uh, so try to imagine this being this, okay? So this is 260, so this is 260, and this is your plate. Okay, you see the plate breaks here at the bolt. Okay, so I hope this one you can try to imagine. So the area is the one which is in contact with the point. Like you can think of it that way. Okay, can I? So 240 comes, sorry, 140 comes from here, 12 comes from the thickness. So this is 12, and this is 140. Okay, let's go back down. Okay, so this one is 140 times 12. Okay, like that. Okay, so this one, right? The formula is just the first step is always to find the A net. Okay, this one you see the A net is just the area of the CHS. Okay, because there are no holes, there are no holes. Okay, there's no holes in the CHS, so it's just the area of the CHS, which is we look at the cross-section table. So go to the top row CHS, top finish. I mean. So top finish, you find 114.3, thickness 6.3. You will get area of 21.4 centimeter squared. Well, for this one, A net is the area of the section, which is 12 times 140. You minus it with the area here, which is got by the bolt. Okay, so what's the area there? So you find the diameter of the bolt, which is 26, times the thickness, which is 12. That's it. Okay, this one is D0. It's the area of the hole, yeah? It's not the area of the bolt. So plus 2, so 26. So in the end, you will get A net is equals to 1368 mm squared. For this one is times 100. Yeah, this one I take from the table. You can try. Okay. Oh, let's see. Pause over this. Now, find the design resistance. So this one, I think they shorten it in the lecture notes, but I'll do it the proper way. So you need to find NPLRD, which is A times Fy divided by gamma M0. So A is 2140, then Fy in this case is 275. Is it 275? Yeah, grade 275. Okay, so 275. 275 divided by gamma M0, which is 1.0. Then this one is in newtons. So I'll make it kilonewtons by multiplying -3, 10 -3. So you have 3140 times 275 divided by 1000. So 589 kilonewtons. That's your NPLRD. Okay, then you need to find your NURD. So you have your NURD. So I think in the lecture notes, they just skip to this, like NURD. Okay, because typically NURD is smaller, typically. That's why I think in the lecture notes they remove this part. Okay, but I'll keep that because that was in the last year's lecture notes. So I'll just keep it. Okay, so this one is just 0.9 times net area. So net area here is so 2140 times FU. So FU is 430 divided by gamma M2. So 1.25. Oh, I forgot to write the formula. Write the formula down. 9 A net FU divided by gamma M2. So this one is times 10⁻3. Okay, so what you get? 600 and oh, it's bigger. Oh, what's that? Oh, because I use A, sorry. Eh? Yeah, right. Hmm. Interesting. Wait, what? Wait. Oh, interesting. Wait, let me check the FU. The FU is correct, right? 430, right? Yeah, it's 430. Okay. It's 663. You check my answer, huh? So the tension resistance is actually the smaller of the two. Because MTRD is the smaller of NPLRD and NURD. So in this case, you will choose 589. Yes, so that's your tension resistance of the CHS. Okay, so now that's done. Just compare it with the tension force. So tension force is 260. So it's bigger, right? So bigger than 260. So the check passes. So okay. So for the plane, it's the same exact step. So find NPLRD, find NURD. Okay, but here we use A, right? So A is 140 times 12. We don't use A net for this one. Okay, so 140 times 12 times 275. Then divide by 1,000, you will get 462. Well, for this one, we use A net, so 0.9 times A net, which is 1368. 1368 times 430 divided by gamma M2 1.25. Make it kilonewtons. Okay, so you will get 424. Yeah, so this one you just take the minimum. So if you take the minimum, you will get 424. So this one is still okay. So done. So those are the checks. So let's go to the last one, which is the fillet welds, 6 millimeters. Okay. So I have no time to cover like the rest of the questions, but so after the welds, right, I just scroll through my solution. Yeah, I think that's okay. So they ask for the weld resistance now. Okay. So for welds, this one you need to have some what's it called? Some 3D knowledge. Okay. So you need to think of this thing in 3D. Okay. First things first, you need to check the side view. Side view, you see the welds, there's one on top, there's one below. Okay. So this one is part C. So these are welds below, welds above. There's also welds 1, 2, 3. Okay, so if you draw it in 3D, it looks something like this. if you draw it in 3D, looks something like something like this. Okay, so this is your CHS. There's a weld here. There's a weld here. There's also a wet weld here. This is your plate. Okay, this is your plate. You don't need to draw in 3D. This one I'm just showing. There's also a weld below. So here, there's a weld below. There's a weld here. There's also a weld below. Okay, so this one you need to think how many, like which part are you welding? Okay, so this one you must think in 3D. Okay, something like this. Okay, so in total there are 6 welds. Okay, so there are 2 methods to do this. There's the directional method. There's also the simplified method. Okay, let's start with the directional method first. The directional method. Okay, the force goes this direction. Okay, so we need to identify 2 things. Which part is the parallel to the force? Which part is perpendicular to the force? So the one that is parallel to the force, we use the FWL RD. For this one, which is perpendicular to the force, use WTRD. Okay, so if you look at this image, let me copy this because I will be needing that. Okay, so for this image, the one which is perpendicular to the force are these 2 welds. 1, 2. Okay, these 2 are perpendicular to the force. So these 2 you use FW TRD. For the 4 welds, for the 4 remaining welds, so 1, 2, 3, 4, this one you will use FWLRD. Okay, then these values you get from the table. Okay, you get from the table. It's much easier. So your filler welds, I think it's 6 mm, right? You give 6 mm. Yeah, 6 mm filler welds. Okay, so 6 mm. So from table. So S275, 6 mm welds. So you go to your table, okay? Go to your table, find the welds. Okay, so it's this page. Yeah, this page. Let me show you. Yeah, this page. I don't know if you can see that, but yeah. That page, so this page, right? So you'll get 6 mm, right? That's the leg length. Okay, this one is the leg length. So for the leg length, you'll get 0.94. That's for the FWLRD and 1.15 for the FWTRD. Okay, so these values just need to, this one is in kilonewtons per mm. Okay, so how to convert it to kilonewtons? You just multiply with the weld length, which is millimeters. So you need to go back to the image. So what's this length? So that length is 150. Okay, you see the length of the weld is 150. Okay, then this one is 140. So 150, 140, 150, 140. So this one is 150. Then you have this one is 140 mm. Okay, so this one again, you need to have like good imagery in your 3D like. Okay, so this one's like length 6 mm. So your total resistance, the sum of weld resistance is 0.94 times 4 times 150. Right? Is the red lines, huh? So 0.94 times there are 4 lines which are 150 in length. Okay, plus 1.15 times 2 because there are two blue lines times 140. That's it. That's your weld resistance in kilonewtons. Oh, okay, so 0.94 times 4 times 150 times 1.15 times 2 times 140. You get 886. So this one is definitely way bigger than your FRD, which is 260. So this one is okay. So this is the directional method. So this relies on the table. There's also the simplified method. So this one is up to you which one you use. Simplified. So simplified method is good if you cannot imagine which part is longitudinal, which one is transverse. So if you cannot imagine these two, better you simplify. Okay, because simplified they don't differentiate parallel or longitudinal. Yeah, they don't differentiate. So for simplified, don't differentiate. It doesn't differentiate this or this. They make the same. Okay. So for this one, but this one right a bit longer, because you need to find manually. Okay, so for this one, you need to find FU first. So therefore, FU is 430. This one is your property of the plate. So this one is FU. Then beta W, so beta W is 0.85. So this one is ST75. Okay. And then beta W you found. Then you find FDWD. Okay, so this one, the formula is FU divided by square root of 3. Then beta W gamma M2. So this one is 430 divided by square root of 3 divided by 0.85 times 1.25. So you will get 430. You get what? So 234. So this one is newtons per millimeter square. Yeah, so that's FVWD. Then you multiply it by the throat thickness. So for a 6 millimeters weld, right? For a 6 millimeters weld, so when this is 6 millimeters weld, right? This is your weld. 6 millimeters is this length. So this one is what we call the leg length. There is also the throat length. So it's this one. Okay, so this one is the throat length. So this one is just, since this is 45 degrees, so you just find divided by, sorry, multiply by sine 45. Yeah, multiply by sine 45. Yep, correct. Okay, so your FWRD, so the weld resistance per millimeters, is your FVWD. So this one is the weld strength multiplied by the throat thickness. So this one is 254 times the throat thickness, which is 6 sine 45 degrees. This one is in newtons. So I'll multiply it by -3. So I'll get kilonewtons. 254 times 6 sine 45. Then divide by 1000. You'll get 0.99. This one is in kilonewtons per millimeters. Okay? So that's your weld strength. So just multiply. So it's the same method as this one. Find the sum of the weld resistance. So the sum of the weld resistance is just your 0.99 multiplied by the total length. So the total length, now they don't differentiate whether it's parallel or perpendicular, it's the same. Okay? So yes, so it's 4 times 150. Whoa, 4 times 150, so copy and paste. Then you also have 2 times 140. There. Then you just add. So it's just the total length times the weld resistance. So you'll get around the same value. 871 kilo Newton should be similar. Yeah, 886, 871, around the same. Okay? So there are two methods to do it. And that concludes the session, I think. Oh, you mean this one, is it? This one. That one, it's not clear here actually. No, because the plate, no, it's not the diameter. If the diameter is like that, the weld should go like this. Oh, it's on 140. Oh yeah, correct. Oh yeah, it's on 140. Correct. Oops. So this one is not 140. This one is the diameter, right? So this one is 114. Okay, if I say it's 114.3, correct. Okay. Yeah, the weld only goes for 114. Oops. So this one is oopsies, this one is 114.3. This one is also 114.3. Okay, so this one is a bit wrong now. Okay, so let's recalculate everything. Okay, thanks for the catch. Yeah, I didn't see that. Okay, that's 827. Then the second one is 820. Very similar to two. There we go. Okay, so that's everything. So yeah, thanks guys for coming. I'll accept questions, but meanwhile, please fill in the feedback form also. Yeah. So thanks guys. Yeah, I'll answer question here. Maybe on yeah. Wait. See how. Oh yeah. Easier. Yeah, thanks guys. So any questions can ask now also. Okay, so what else did I miss? Split is not in. Theory questions you can try. These types of questions, I don't know if it will come out. These types. Like, will this kind of question come out? I'm not sure. Yeah, this one you can refer to the PYP. Okay, then because this one, like, no, it's a bit more complicated. Yeah, because this one, right? This one is obvious. The force is 260. Like both the bearing and the shear, they are 260. But for the example just now, right? You cannot just simply just take 160. Okay, 160 is the shear force, but there's also the tension, right? Because if you're an L like this, right, then you put force, right? It feels like this, right? So the tension force is not that simple. Yeah, I don't know if this will come in or it's, the what? No, this one is that's the question. The Is this so? Yeah, is this in the lecture notes? Can you like check? Yes. Oh. Oh, he never really oh, they have the synthetic and the structural analysis. Yes, correct. We should be very good. Share the concept. Attention is attention is basically the market. So yeah, for this one, 1920. You know, 1920 something. Yeah. Let me see. Let me check this. I think I've done it before. This one. It's 1920. It's very old. Yeah, so I'm not sure it will come out. Yeah, I don't know if you got this one. That's why I'm not sure. Yeah, it's that one. So I think just to give you an idea, because okay, yeah. So for this one, right, you have 160, right? Then you have 6 volts. So your shear force, okay, shear force per volt is 160 divided by 6, right? Then you just compare it with your MV RD per volt. Okay, this one is the table one, so you just take the table, check the table. Okay, that's for shear force. Then you have the tension. So for tension, if you have 160, right, put here, then you have your eccentricity, right? So this whole thing will rotate about A. Okay, this whole thing will rotate like this. Okay, can you imagine that, like rotating like that? So if you notice, the topmost bolt gets the most tension. Okay, so we just need to check the topmost bolt. If the topmost bolt fails, then everything will fail. Okay, so that's the idea of the check. Okay, so that's why they draw it like this. So bottom bolt will be poked a little bit. This one will be poked more. This one will be poked most. So like this. So that's your diagram. It's something like this. Then this is your bottom. So where's my cheat sheet? Let me see. Here. No question, right? Yeah, but I'm not sure. Yeah, I'll just teach you. It's okay. So the question is, how much is the tension force at the top, right? Because the tension is maximum at the top. Okay. So this one is Y1, this one is Y2, this one is Y3. Okay, it's from the center of rotation to each group. Okay, that's y1, y2, y3. So in the formula, I think they give that FD, F tension of top book is equals to P times E. So this one is the moment, right? P times E times y1 divided by 2 times sigma of y I squared. So this one means P is 160, E is 90, right? E is 90 times y1. Y1 is from the center of, oh, sorry, I flipped. Sorry, I flipped this. This is y1, y2, y2. Sorry. Y1 is from to the top group. Okay, so y1 here is 40 plus 60 plus 160. So that's 160. Okay, this is 160. So y1 is 160 divided by 2 times. So you have 160 squared plus y2, right? So y2 is 140, right? Oh, sorry, 160. Y2 is 100. Then y3 is 40. Okay, so 140. So 100 squared plus 40 squared. That's your tension force. So this one you compare it with what's your book there? Let me see. With the tension resistance. Tension resistance. So this one you get the value, right? Compare it with your tension resistance. So it's FT RD. I think this one you can find from the table as well. So you don't need to calculate. Yeah, find from the table. So this one is what? M16 class 8.8. So 8.8 class M16. FTRD is 90.4. Okay, 90.4. 90.4 kilonewtons. Well, FBRD, right, is 60.3. So you can actually calculate now. I'll just find out. 160 divided by 6 is 26.7. Okay, so this one is okay for the shear. Then for the tension, you will get 30. So 31. So it's less than your FTRD. So it's okay. This one just in case they ask now. So this one is also okay. So this one is also okay. Then you have the combined resistance. Okay. So this one is tension force. This one is shear force. Then combined check. Combined check. What's the combined check? Is yes, FDED divided by FBRD plus 1.4. Sorry, one FDRD. Sorry, FTED divided by 1.4 FTRD. So this one is 26.7, 60.3, and we have 31, 1.4 times 90.4. So this one is, I think, definitely less than 1 million. 26.7, 3.3 plus 31, 1.4 times 90.4. 0.69. So this one is less than 1. So this one is also okay. So that's how you do it. So very fast. Nah, this one is the classic example. It's not this. It's not this. Yeah, so this one is only for I wouldn't. Okay, yeah, angle lah, but it's different from the angle tension member. It's different. Okay, this one is under connection. Sorry. Yeah, yeah. This one is part A. Okay, so yeah, the tutorial is similar to this one. Yeah, it's more similar to this one. This one is 1920. This one is 2021. Yeah, the one I did was 21, 22, I think. Yeah, 21, 22. Hmm. What else? This one is I think 21, 22 also. Yeah. This one was my year. Loyal. Yeah, but yeah. So yeah, I think nothing much. Eh? Yeah. So anything else? Yeah, I think nothing much. Yeah. So you can try. Okay. Yeah. Okay. So if there's no question, then I guess I can end the Zoom. Yeah? So thanks, guys. Bye bye.